the last talk of the day, we are going back to a natural science, physics. Our speaker is Scott Aaronson from MIT. When one of the first times I met Scott, he told me why he was interested in physics. It's because, as a kid, instead of playing computer games, he was learning physics because he thought the world is like a computer game, but it has much more realistic special effects. Scott was a postdoc in my group at IIS some years ago, and I can tell you lots of stories, more stories than I can tell you about the other speakers, but I won't. I mentioned, first of all, he just published a book that you should get. It's called Quantum Computing Since Democritus, and that's going along a course that he's taught for several years at MIT and in Waterloo, which is much more than just a book about quantum computing. And the last thing I want to mention is his blog. He's an extremely popular blogger. Most of the topics have to do with the boundary between physics and computation, but you'll find there practically anything. And I just remember that I mentioned the Google algorithms, PageRank and Hits algorithm of Kleinberg. Just as an example, you can, of the blog, issues or the quirky mind of Scott is, you can read his blog post on eigenmorality evolving from this Google algorithm. So anyway, let me ask you to welcome Scott Aaronson.
Okay, the mic is on. Okay, so thanks so much, Avi. It's great to be back here. So I'd like to tell you about computational phenomena in physics. Now, when I did a Google image search for a quantum computer, this is one of the first things that came up. For all I know, maybe that's what they look like. I mean, I'm a theorist. I'm not an engineer. This is one of the few places where I guess I don't have to apologize for that. The one other thing that I wanted to do, just in order to continue the convention that was established this morning, here is John von Neumann. Not only did he, here at IIS, build some of the first electronic computers, but he was also one of the great systematizers of quantum mechanics. So much so that, many people have pondered the question, why did von Neumann not invent quantum computing back in the 1950s? And the only answer to that seems to be, well, he had a lot on his plate and he didn't get around to it. Okay. All right, so my starting point is that, there are certain technologies that would be great, but that we, never seem to see. First of these, warp drive. Where is it? We've been waiting. I even, just saw the movie Interstellar. I would settle for a wormhole. Perpetual motion machine. Where is it? Okay, and then the third is what I'm going to call the Uber computer. This is a device that. It doesn't necessarily tell you the meaning of life or anything like that, but any well-posed mathematical question, it just instantly tells you the answer to. So just Goldbach's conjecture. So okay, so now in the first two cases, we know something about why these sorts of machines haven't been built, right? It's not just a matter of engineering difficulty. It's really something fundamental about the laws of physics. In the first case, it's special relativity, or we could say, the causal structure of space-time. In the second case, it's the second law of thermodynamics. Okay, and so what I wonder about is, what about the third case? What are the fundamental physical limits on what can be feasibly computed? Moreover, do those limits then have any implications back for physics, as is certainly true in the first two cases? Okay, so as Avi sort of eloquently told us this morning, sort of the first pass we could make at an answer to this question is the Church-Turing thesis, or its sort of modern complexity formulation. So the Church-Turing thesis basically said that any physically realistic computing device can be simulated by a Turing machine. The extended Church-Turing thesis, or ECT, adds the proviso with at most a polynomial overhead in time and memory. Okay, so and it hedges a little bit on whether the simulation has to be deterministic or whether it can be probabilistic. But as Avi, among others, has taught us, those are very likely to be the same thing anyway. So so this is a very extremely audacious thesis. The extended version, much even more so than the original one. And so it behooved in really bridging the two worlds of computer science and physics, because it's talks about computability, but ultimately, of course, this is really a question about nature. We could imagine a universe where the halting problem was solvable for free. That just doesn't seem to be the physical world that we live in. Okay, so then it behooves us to ask, well, how sure are we of this extended Church-Turing thesis? What would it look like for it to be overturned? What would a challenge to this ECT look like? Well, so let me run you through, a few sort of just purely classical examples of what challenges to the extended Church-Turing thesis would look like. Okay, so the first, here's a really nice old proposal from the 1970s. Okay, that you could just take two glass plates and put pegs between them in whatever pattern you like, and then dip the resulting configuration into a tub of soapy water, and then take it out. Okay, and you'll find soap bubbles that are forming between the pegs, and like any bubbles, they'll try to sort of relax to a minimum energy state. In this case, the minimum energy state ought to be what we would call the minimum Steiner tree, which is just the minimum total length of line segments connecting these points in the plane, where the line segments could meet at intermediate points like these. And now, there's something curious about this, which is that minimum Steiner tree is well known to be an NP-hard problem. Okay, so which means that one could take any other combinatorial search problem. For example, find me a proof of the Riemann hypothesis in first-order logic with at most 100 million symbols. And one could encode that problem into a suitable configuration of pegs that you then dip into your soapy water. So then one wonders, if one does this, what will happen? That has one then just sort of force nature to prove the Riemann hypothesis for you, or do what our both our greatest human brains and our great fastest computers have thus far not been able to do. So so there was a discussion about this on the internet a decade ago, where some people said, well, yeah, a lot of people think that this wouldn't work, but this is just sort of an academic dog. This just shows computer scientists' narrow-mindedness, right? That they I bet not one of them ever tried it. So the comment actually led to the one foray into experimental physics in my life. So I. It was a pain getting this thing through airport security. I used to, bring it around and demonstrate it. But it's a really cool experiment. You should try it at home. When you have only 3 or 4 pegs, what you find is that typically the soap bubbles do relax to the minimum Steiner tree. They do solve this kind of cool optimization problem. Okay, then you start adding more pegs: 5 pegs, 6 pegs, 7 pegs. And then what you start to see is that the bubbles can get stuck in a suboptimal configuration. Okay? And in fact, sometimes they'll form a structure which is not even a tree at all. It contains an intermediate cycle, which then proves that it can't be optimal. Okay? So So indeed, it seems that, I mean, I didn't try every possible brand of soap, but, there's some evidence that nature is not solving, NP hard problems by magic in this sort of way. Now, this may sound silly, but, again and again, you will read things like, including in, serious scientific papers, well, like proteins, when they fold into their lowest energy configuration, they're solving an NP hard problem. Okay, and like anytime you hear something like that, you ought to be asking yourself, what's the catch? Okay, and in this case, in the case of protein folding, the catch is very interesting. It's that, well, first of all, there was extremely strong selection pressure on proteins to evolve in such a way that that they fold pretty easily. I mean, a protein for which you had to prove the Riemann hypothesis to figure out how to fold it would just not be a very good protein. Okay, but even then, there are proteins that fold into suboptimal configurations. So prions, which are the agent of mad cow disease, appear to be an example of that. Okay, so, but, in general, physicists know that, systems in nature can get stuck in metastable states. I mean, if you put a rock on some crevice on a mountainside, it could reach a lower state of potential energy by rolling up first and then rolling down. But, it's rarely observed to do that. So, with the soap bubbles and with the proteins, it's, maybe it's more abstract, but I think it's ultimately a similar story. Okay, but now, so if not that, I mean, you've all heard about quantum computers, and we'll get to that. But, what about the neglected other great theory of the 20th century? What about the relativity computer? Okay, so the idea of the relativity computer is extremely simple. It's that you would start your computer just working on some, extremely hard problem of your choice. Then you would leave your computer on Earth. You would board a spaceship, which is traveling at very close to the speed of light. You would fly around, then you would decelerate. You would return to Earth. Now, in Earth's frame, billions of years would have passed. Civilization would have collapsed. Or, your friends would be long dead. But, if you could somehow still find your computer and it was still, hadn't been incinerated by the sun or whatever, then, you could read out the answer to your hard problem. Okay, so, this raises an obvious question, which is, well, why don't people try this? Well, I mean, if you're worried about your friends being dead, just bring them on the spaceship with you, right? So, well, okay, or, more seriously, we can ask, is there any problem of principle, to doing this? And I think, the very interesting answer is yes. I mean, when you look at just, again and again, we find that, if you just look at one or two aspects of the laws of physics and ignore all the others, it can look like you get these sort of unbounded computational speedups. And then you take into account what else we know about physics, and and those things put constraints. So in this case, I would argue that the key thing that we've ignored is energy. Okay, how much energy does it take to accelerate to that close to the speed of light that you would get an exponential computational speedup? Well, you can calculate that. You find that you would have to, go so fast that the difference between your speed and that of light would be exponentially small. Okay, to do that requires an exponential amount of energy, which means, just to fuel up your spaceship, that already takes exponential time. Or even for the fuel from the faraway part of the tank to sort of send a signal to you, to affect you, takes exponential time. So we've sort of traded one exponential blow up in resources for a different one. Okay, and this is, I think, a very paradigmatic example. Okay, so now another example I'd like to talk about is what I'll call Zeno's computer. There's actually an entire literature on something called hypercomputing. Okay, and the basic idea of all of it is this. Wouldn't it be great if we could build a computer that just did the first step of its operation in 1 second, the next step in half a second, the next step in a quarter second, next in an eighth second, and so on, so that after 2 seconds it would have done infinitely many steps. Again, we can ask, why don't people try it? And, and in this case, I think the answer is that in some sense they do try it. I mean, there's a whole community of people who try to overclock their microprocessor, right? They run it at a faster speed than it's, supposed to be run at. Okay, but many of you might know the danger in doing that, which is that if you run your processor too fast, then it will overheat, it will melt. This is why your computer has a fan. This is also why supercomputers are often cooled using liquid nitrogen or whatever. Okay, so in general, one once again finds a trade-off. Okay, that the faster you would like to safely run your microchip, the more it has to be cooled, the closer it has to be to absolute zero. The more you want to cool it, the more energy that takes, the more energy you have to pump in. And we could ask, what is the fundamental limit here? How fast, in principle, could a computer be run? Okay, well, you could say, strictly speaking, we don't know, but actually, physicists have a pretty, a good idea of where, you're probably going to run into a fundamental limit. So, if you were to run your computer so fast that it did more than 10 to the 43 operations per second, or about, one operation per Planck time, then, one can calculate that one would have to concentrate so much energy into so small of a space in order to run it that fast that your computer, this energy would gravitate. Your computer would exceed what's called the Schwarzschild limit, which means that it would collapse to a black hole. Okay, so, I've always liked that as nature's way of telling you not to do something. Okay, now, another nice idea is the time travel computer. The idea here is very simple. There's this standard thought experiment where what if you could just go back in time and dictate Shakespeare's plays to him? And so then he would say, "Oh, thank you. Now I don't have to write them anymore." And so then he would just crib the plays from you, and then he would publish them as his own, and then they would come down to you. Now notice that this is actually very different from the famous grandfather paradox, because there's no actual logical inconsistency in this story, right? You get the plays, you send the plays back, everything's consistent, right? If you like, the only paradox here is one of computational hardness. Somehow Hamlet appears without anyone ever going to the trouble of writing it. Okay, and actually, again, the movie Interstellar has a. Well, all right, I shouldn't give away the ending. Sorry, but okay, but it should come as no surprise that if we lived in a world with closed time-like curves, then one could generically exploit a similar effect to solve hard computational problems. So, for example, if you had some NP-complete problem, then you could just feed in one guessed solution into your closed time-like curve, and then have a computer inside the closed time-like curve, which checks if the solution is correct. If it is correct, then just sends it back in time unchanged. And if it's incorrect, then increments it by 1 and sends that back in time. Okay, and now we say, look, in order to prevent a grandfather paradox, nature has to find some sort of consistent evolution around the closed time-like curve, right? But given the rules I just said, the only consistent evolutions are the ones in which a solution to your NP-complete problem just miraculously appears inside the closed time-like curve. Okay, so in fact, one could do even more using this technique. So John Watrous and I had a paper where we worked out exactly what could be done. We showed that you could in fact solve p-space complete problems using only a polynomially long computation inside of a closed time-like curve. On the other hand, you can't do more than that. Not even with a quantum computer, in case you were wondering. So this is not the paper I based my tenure case on, by the way. But. Okay, all right. But at some point, I should come to quantum mechanics, and here, many, I think many people, have gotten the impression that quantum mechanics is somehow, complicated, hard, or something. I mean, okay, if you want to know, the ground states of, interesting molecules, or, you want to do quantum field theory, yes, that can get complicated. But, the big secret, I think, has come out more and more in the last couple decades, is that quantum mechanics is actually incredibly simple once you take the physics out of it. So, the way that, in computer science, the way that we tend to look at quantum mechanics through the computational lens is that it's just a certain generalization of the laws of probability. Okay, it is. It's sort of, if someone asked you to invent something which was like probability theory, but instead of being based on real numbers between 0 and 1, it should be based on complex numbers. And instead of being based on the 1 norm of vectors, it should be based on the 2 norm. Okay, then they've more or less forced you to invent quantum mechanics. Okay, and so like by that reasoning, I like to imagine that mathematicians could have come up with this by pure thought. In fact, they didn't, but in some alternate universe, they did. Okay, so a little more detail. Probability theory, is a theory where you describe you describe your state of knowledge about a system by a vector of non-negative real numbers, which all add up to 1. And then if something happens to the system, then you change your representation of its state by taking that vector and multiplying it by a matrix that always maps probability vectors to other probability vectors. We call that a stochastic matrix. Okay, quantum mechanics, almost the same thing, except now our vectors are vectors of complex numbers where, that have unit norm. The sum of, their squared absolute values is 1. And if something happens that changes the system, then you multiply this vector by a matrix that always maps unit vectors to other unit vectors. We call such a matrix a unitary matrix. Okay, and then the one other thing to say is that if you look at the system, that you're going to see the ith outcome with probability equal to the absolute value of alpha I squared. Right, those are, and furthermore, you then look at it as, if you see it in the state I, you look at it a second time, it will still be in state I. It's made up its mind. Okay, so, you're looking, collapses the state. Okay, those are the rules of quantum mechanics. Okay, but what about quantum computing? All right, well, if we think about it, what quantum mechanics really says is that you've got to assign one of these complex numbers, we call them amplitudes, to every possible configuration that a system could be found in on measuring it. Okay, so if you had a computer with n bits in its memory, what this is saying is that you would have to describe its state in general using a vector of 2 to the n amplitudes. Okay, 1 for every possible string of bits. And this is just the notation that physicists like to use for vectors. It's called the Dirac-Ket notation. And some of us, and I think this is like the single greatest hurdle for computer scientists to overcome in learning modern physics, is that you have to write vectors this way. Okay, but you really get used to it. It's really a good notation. Okay, so now this the fact that just to so what we're saying is that just to represent a general state of 1,000 measly particles, nature sort of off to the side somewhere sort of has to be writing down 2 to the 1,000 complex numbers on some scratch paper, right? And then anytime something happens to these particles, all of these 2 to the 1,000 numbers get crossed off and replaced by new numbers, right? I mean, this is more numbers than there are particles in the observable universe. Okay, so this is really a staggering claim about about the physical world. Maybe it's even the most staggering claim that quantum mechanics makes, and it's sort of amazing that although there are people like Schrodinger who sort of recognized this already in the 1920s, it took a long time for, I think, just the full enormity of this to really sink in on people. So chemists and physicists actually, recognize this for quite a while, mostly as a practical problem. If you're trying to simulate quantum mechanics on a classical computer, for example, because you want to know what the rate at which some chemical reaction is going to happen, then, you've got to double the size of your simulation with each new particle that you add. Okay, and so, chemists and physicists invented all kinds of incredibly clever tricks for trying to cope with that exponentiality. Some of them, like the density functional theory, were, rewarded with Nobel Prizes. Okay, but, it was really Feynman, I think, who brought to everyone's attention, this, in retrospect, absolutely fundamental question, well, which is, is there any way to avoid this exponentiality, right? Is there a fast classical algorithm to simulate quantum mechanics which would work in general? And if there isn't, then why not turn that on its head? Why not then build computers that would themselves exploit the same principle of quantum superposition? And that now, okay, you could ask, supposing we did that, what would those computers be good for? Well, Feynman was able to give only one example. They would be good for simulating quantum mechanics. That sounds kind of silly, but I think that if we do ever get practical quantum computers, that will still be the most important real application of them, okay? Because quantum simulation, as I said, is something that has huge applications to, designing better photovoltaics, to understanding high-temperature superconductivity, to understanding protein folding, to maybe designing new, biomolecules, new drugs, to, understanding high-energy physics. Okay, so, and, lots and lots of computer time is used today for, trying to simulate quantum mechanics, and we are very, very confident that a quantum computer, if built, could give you very significant speed-ups for that. Okay, but the question remains, can a quantum computer solve any classical problems faster than a classical computer could do it? As many of you have probably heard, Peter Shor showed 20 years ago that, there is an example of that. A quantum computer could find the periods of exponentially long periodic sequences in polynomial time. And that sounds a little abstruse, but that has certain applications, such as factoring integers, discrete logarithm, thereby breaking essentially all of the public key cryptography used in the world today. So that made people interested in this, subject who hadn't been previously. Okay, so now, the obvious question that anyone asks is, well, okay, but can quantum computers actually be built? They already have been. Quantum computers have successfully demonstrated the factoring of 21 into 3 times 7 with high statistical confidence. That's, after only, about $1 billion of effort in this field. My experimentalist friends, hope to be able to do 35 before too long. Okay, so, so then, people ask, well, okay, well, why is scaling it up so hard? But there's a very, very well understood answer to that. It's because of something called decoherence, okay, which basically just means unwanted interaction between a quantum computer and its external environment, which sort of prematurely measures the quantum state and forces it back down to being classical, sort of, before you were ready to measure the answer. Okay, so I should, say something here. The way that a quantum computer would work, right? It's a computer whose state would be, this superposition state, this gigantic vector of amplitudes. Okay, and the entire idea of it is that you would try to choreograph a pattern of constructive and destructive interference between these amplitudes, right? Where you would get all of the different sort of paths that lead to each wrong answer. To some have positive amplitude and others have negative amplitude, so that on the whole they mostly cancel each other out. Whereas the paths leading to the right answer should reinforce each other. Okay, so that's, it's a very subtle kind of very delicate effect that you're trying to go for. Shor showed, amazingly that for the factoring problem, you can actually choreograph the right kind of interference pattern. You can get it to work, by taking advantage of very sort of special mathematical properties of the factoring problem. Okay. However, if the computer were to interact too much with its external environment, sort of before the end, then it would no longer be in a superposition state. Okay, it would merely be in just a classical probabilistic mixture, which means it's just in one thing or it's the other thing, right? So like when any when most popular books, talk about like Schrodinger's cat, for example, right? They say, they basically just say, look, there's some cat in a box, and you don't know whether it's alive or dead, and then you open the box, and then you find out. This by itself is not, surprising. Okay, let's be clear about that, right? If that were all there was to quantum mechanics, then people would not be yammering on about it for 100 years. Okay, the interesting part, of course, is that you can do a different kind of experiment where the two different branches of the cat, the alive and the dead branch, would interfere with each other. They would each, because these amplitudes, work in a different way than classical probabilities do. Because they're based on the 2 norm rather than on the 1 norm, they add up in different ways. And, they could, for example, cancel out and, cause, certain outcomes, that you would have expected classically not to happen at all. Others to happen with much greater probability. So, but now if someone is looking at your quantum computer as it's operating, then it's it reverts to being in a classical state. So it's as if the cat is merely either alive or dead, and you don't know which, or it's as if you merely had a classical computer with access to a random number generator. Okay, and and again, I think it's really unfortunate the way that quantum computing tends to get described in the popular press, because it again doesn't sort of differentiate quantum computing from that, really. Like I'm sure that you've seen articles where it says, well, the way a quantum computer would work is just by trying each possible solution in a different parallel universe. Okay, well, the trouble with that is yes, you could do that, but then when you make if you did, you can create a superposition over all the different answers. But if you did that, and then you measured, then you would simply see a random answer. And if all you wanted was a random answer, you could have just picked one yourself with a lot less difficulty. Okay, so again, everything depends on this effect of interference, and interference depends on your quantum computer being extremely well isolated from its external environment. A few, in fact, there are even a few skeptics, the problem is so hard that a few skeptics in computer science and physics, have argued that it must be fundamentally impossible, right? So in fact, in the 90s, this seemed like it might be true, right? That, that you could never keep anything perfectly isolated from its external environment for too long. Certainly not something as big and complicated as a computer factoring a number, right? So how is this ever going to work? Okay, so then, in the, a few years later, an enormous discovery was made, which was called quantum fault tolerance. Okay, so what was found is that actually, in order to do quantum computation, you don't have to keep your computer perfectly isolated from its environment. Basically, it's enough to keep it pretty well isolated, okay? Even if every qubit at every step, at every time step has, say, a 1 in 1,000 chance of just being measured or, collapsing, having its state collapse, you can correct for that. You can encode your, the stuff you care about in very non-local degrees of freedom, sort of spread out across many qubits using very, very clever quantum error correcting codes. You can then repeatedly make measurements that will tell you whether an error has happened or not, but that won't tell you the state of your computer, which of course you don't want to know. Okay? And if an error has been made, then you can correct it, thereby preserving the quantum information for an arbitrarily long time. Okay, now, in order to do this, you've got to be able to get the decoherence down to, sort of a certain critical point where, which we're not at yet. Okay, at least not in a scalable way. Okay, but, the experimentalists are orders of magnitude closer to that point than they were, let's say, 15 years ago. Okay, so I think that's really the right metric to be looking at right here, and not the metric of how large a number has been factored. It's kind of like, I don't want to use the analogy, but like building a nuclear weapon, right? You build half of, you have half a critical mass, you don't get half an explosion, right? So, so the real goal here is to control the decoherence well enough that you can start doing error correction, where you're correcting the errors, correcting the decoherence faster than you're introducing more decoherence into the system. And once you pass that point, then if physicists understand quantum mechanics like they think they do, then at that point you ought to be able to just scale up to as many qubits as you want, and operating for as long as you want. Okay, now there are skeptics who understand all that, but they say it's still never going to work. Okay, because there must be some kind of highly correlated decoherence that violates the assumptions of these fault tolerance theorems. Or if not that, then it must be that quantum mechanics itself is going to break down just in order to prevent quantum computers from working, because it's just too implausible, right? And so at that point, the only thing that I can say is, well, I really hope you're right, okay? Because if you're right, that's 1,000 times more exciting than if quantum computers merely turn out to be possible. Okay? Now I tend to be a scientific conservative, right? So I'm betting on the more boring possibility, which is, yeah, we can probably just build quantum computers, if we care, if we care enough or want badly enough to do it, they'll probably work as the theory says. Okay, but, if not, then that, we would have to rewrite all the physics books to explain why not. And, and actually for me, I like to say that, the single most important application of a quantum computer, even more important than quantum simulation, is disproving the people who said it was impossible. Okay, the rest is icing, right? If we could spend, $11 billion to find the Higgs boson, right, then certainly, to put quantum mechanics itself to this most severe test that it's, ever been put to. And by the way, we talk about the computational lens, right? If trying to build a quantum computer led to a revision in quantum mechanics, that would be like the most staggering contribution of computer science to physics that you could possibly imagine. I don't expect it to happen. Okay, but now let me come to a really key point, okay, which is that, even today, after we've, some of us have been sort of, trying to explain this for 15 years, lots and lots of people seem to have the impression that a quantum computer would just solve any NP-complete problem that you want in polynomial time, okay, that's what it would do, okay? But it's crucial to realize here that factoring the problem that Shor solved is neither known nor believed to be an NP-complete problem. Okay, it has, very, very special properties, like, the least of which is that, every positive integer has exactly one prime factorization, which Euclid proved 2,300 years ago. Okay, but, lots and lots of number theoretic properties that seem to prevent it from being NP-complete. Okay, and today, most of us actually don't believe that quantum computers will, in general, be able to solve NP-complete problems in polynomial time any more than we believe classical computers can. I mean, now, not surprisingly, we have no proof of this, because we can't even prove classical computers can't solve them. That's the P versus NP question. Okay, but Once you understand how quantum algorithms work and the need to rely on this very, very subtle interference effect, it looks kind of, almost as implausible that they could solve NP-complete problems as that a classical computer would be able to do it efficiently. Okay, one thing that we do know here is an important result of Bennett, Bernstein, Broussard, and Vazirani from the 90s. And what they showed is that if you just threw away all the structure of an NP-complete problem and just thought of it as an abstract space of 2 to the n possible solutions, where the only thing you knew how to do was to query a black box that for each solution just told you whether it was correct or not. Okay, and now the only catch is that you're allowed to ask this black box a superposition of questions, and get a superposition of answers, and you can do that repeatedly. Okay, in this case, we can show that even a quantum computer will need exponential time to solve an NP-complete problem in this way. Specifically, it's going to need at least 2 to the n over 2 steps. Okay, where, compared to the 2 to the n steps that a classical computer would need, because it's just, in this case, it really is just looking for a needle in a haystack. Okay, now very, very interestingly, this 2 to the n over 2 turns out to be achievable. So you may have heard, after Shor's algorithm, the second most famous quantum algorithm is called Grover's search algorithm. And that one searches any list of, say, m elements in only about square root of m steps. Okay, so it doesn't achieve an exponential speedup, right? It merely achieves a square root speedup compared to what you could do classically. So that, that seems less impressive than Shor's algorithm, but its range of applicability is just enormously wider. Okay, it applies to sort of any kind of search task whatsoever. Okay, but of course, the square root of 2 to the 10,000 is 2 to the 5,000. So, so this is not turning exponentials into polynomials. Okay, so now, if we really wanted to solve NP-complete problems in polynomial time using a quantum computer, then we know that from Bennett et al. That we would need an algorithm that somehow exploited their structure, just as a classical algorithm would have to. Okay, and this is where the story gets really interesting, because there is a beautiful proposal for a quantum algorithm that would try to solve NP-complete problems quickly by exploiting their structure. It's called the quantum adiabatic algorithm. It was invented about 15 years ago by my colleague Ed Farhi and some of his collaborators. Since then, they've just, been trying to understand what it does. You can think of this algorithm as like the quantum version of simulated annealing, if you know what that is. So it is a heuristic algorithm. It's not guaranteed to work. In fact, as I'll show you, there seem to be, definitely cases where it doesn't work. But it's something that you can try out, to see what happens. And so the idea is that you start out by applying certain certain interactions to a collection of qubits, what physicists call a Hamiltonian. For me, a Hamiltonian is just the thing that you raise e to get a unitary matrix. So you start out by applying a certain Hamiltonian, and now in physics systems like to live in the ground state of their Hamiltonian, which means like their lowest energy configuration. Okay, so you have your system start out in the ground state of its initial Hamiltonian. Okay, and then you slowly vary what Hamiltonian you're applying. So like, this might mean like just slowly changing what magnetic field you're applying to, a collection of spins in your spin lattice, for example. And you end up applying some final Hamiltonian, HF. But HF is designed so that its ground state encodes the solution to an NP-complete problem of interest to you. Okay, now there's something called the adiabatic theorem, which says that as long as you transition between HI and HF slowly enough, you're going to always stay in the ground state, which, or near the ground state, which means that you're going to end, very close to the ground state of H sub f, and you're going to get the solution to your NP-complete problem. Okay, so from this perspective, the only question is, how slowly do you need to vary the Hamiltonians? Okay, so now many of you, may have read about a company called D-Wave in Vancouver, which has actually so far spent more than $150 million toward, building sort of special purpose quantum devices, which are just for trying to implement, some version of this adiabatic algorithm. Okay, they call it quantum annealing because it's like the adiabatic algorithm, but sort of noisier at a finite temperature. So there are a lot of questions and a lot of sort of debates people have been having about these devices. You may know that they've sold 2 of them, one to Lockheed Martin, the other to Google. And because of that, there have now been independent studies done on these devices. So we know a lot more than we did just a few years ago about what they're doing. Basically, there are 2 big issues to keep in mind, when discussing the D-Wave devices, right? The first is the hardware issue, right? And this is what everyone wants to ask about. Is it a true quantum computer or not? Okay, right? And that's well, it's sort of a semantic question, right? Because so it is a computer. It's a device. It is able to. What it does, it has a chip inside. I've actually walked inside of it. It has most of it is a cooling system. It cools down to about 20 millikelvin, and then in the middle there's a chip with some superconducting Josephson junction qubits, and the latest model has about 500 of them, and they try to, using this adiabatic evolution, they try to sort of relax to their lowest energy state, thereby solving some optimization problem that you encoded into the chip by setting the couplings between adjacent qubits. Now, it definitely does produce solutions to the optimization problem that, are often, pretty good. And there are definitely quantum effects that are relevant at some level to explaining what this device does, certainly at the level of 1 qubit, probably even, at the level of 8 qubits. Okay, there is no evidence so far that this device is doing anything faster than you could do it with a classical computer, or for that matter, as far as we've seen in public anyway, that the scaling behavior looks different. Okay, so now part of that, and this is sort of consistent with what a lot of us sort of thought from the beginning. Not that many people listened, but the the obvious issue here is is the one of hardware, right? That the qubits that they have are only staying coherent for a matter of nanoseconds, so there's a lot of sort of noise in the system. You're not really doing this true, adiabatic evolution. Okay, but and actually some of you may have heard that Google recently invested in the group of John Martinez, which has superconducting qubits that have 10,000 times the coherence time of D-waves, although they haven't yet integrated a large number of them. Okay, so so these hardware issues may ultimately be solved by just getting better and better qubits. But to me, the even deeper issue is the algorithmic one. Okay, suppose forget about D-waves. Suppose you had a perfectly functioning, perfectly coherent quantum computer, and you ran this adiabatic algorithm. How much speed up could you expect for NP-complete problems? Well, we still don't, even there, we still don't know that you would see a real speed up. And in fact, people have done very careful numerical studies of this. And what determines how long you have to, how much time you need to take in transitioning between these 2 Hamiltonians is what's called the minimum eigenvalue gap. the minimum gap between the smallest and second smallest eigenvalues of the Hamiltonian. And if this ever gets exponentially small, then you need to run the algorithm for exponential time. Okay, and when you look at, let's say, random instances of 3-SAT or of some other, a canonical NP-complete problem, you sometimes find that indeed this gap gets exponentially small. It looks like these two lines, are touching each other, but not quite. So, when Fahey sort of started to notice this, he told me that he asked an expert in condensed matter physics, well, based on your experience with, similar systems, because condensed matter physicists have like a century of experience studying these spectral gaps, he said, do you think that this gap is going to decrease polynomially or exponentially with the number of particles in our system? And the expert thought about it and said, I think it's going to decrease exponentially. And of course, that wasn't the answer that Fahey wanted to hear. So he said, why do you say that? And he said, well, it's because otherwise your algorithm would work. Okay, so I think that there's actually something deep there, which is that once we've seen enough examples of sort of nature, trying to prevent us from solving NP-complete problems, we might just sort of turn things around and just say, let's say we start from the premise that NP-complete problems are hard. What implications does that have for other issues? Okay, and so, we might even, formulate something that, I'll grandly call, the no super search postulate. So Avi talked before about P not equal to NP as a natural law, right? Here, I want to go further than that. I want to say, I conjecture that there is no physical means to solve NP-complete problems in polynomial time. I mean, because I'm a computer scientist, I call this a conjecture. I've learned that there's a cultural difference. Physicists would call this a law, okay? But, so, this would include P not equal to NP as a special case, but it's stronger. And it's no longer a purely mathematical conjecture like P not equal to NP, but also a claim about the laws of physics. And now, suppose we invoke this, what would it explain? It would explain, as I said, why the adiabatic systems have small spectral gaps, why does protein folding and all these other, spin lattices get stuck in metastable states. Why is the Schrodinger equation of quantum mechanics precisely linear? It turns out one can show that if there were even the smallest nonlinearity in the equations of quantum mechanics, so like if the evolution of the vector of amplitudes could be, a nonlinear transformation, okay, then one generically could solve NP-complete problems in polynomial time. One could also then send signals faster than light, okay, so one could do a lot of amazing things, but, the hardness of NP-complete problems is sort of, if you like, another reason why we should be suspicious of that. Why are there not closed time-like curves? Okay, but, I know you're asking, but can computational complexity engage even more deeply with the content of modern physics? What other new insights has it given the physicists? So thank you for asking that. I'll give, a few examples. Some people have asked, well, could quantum computing sort of help us resolve which interpretation of quantum mechanics is the right one? Okay, well, so David Deutsch, who is the sort of, along with Feynman, one of the founders of quantum computing, has a famous argument for what's called the many worlds interpretation. Many worlds is what says that, all of these different branches of the superposition are equally real, and every time you measure a quantum state, you are literally splitting into two parallel copies. Despite how it sounds, this is in some sense the conservative interpretation of quantum mechanics. This is just sort of the one that, where you don't have to add anything to the math. That's just sort of what the math wants. And, Deutsch goes a little further. He says, to those who still cling to a single universe worldview, I issue this challenge: explain how Shor's algorithm works. When Shor's algorithm is factored a number using 10 to the 500 or so times the computational resources that can be seen to be present, where was the number factored? How and where was the computation performed? So, I think this is an interesting argument. Well, there's also an interesting, I don't view it as decisive. There's an interesting response that I'd like to suggest, which is, to those who cling to a many-universe worldview, we'll explain why can you only do factoring? Why are the NP-complete problems still hard? You might think that if every universe could just try out a different solution, then, NP-complete problems would be easy. So maybe, quantum mechanics is like this intermediate possibility that just none of our sort of pre-quantum language is a very good fit for. Okay, and there are other sort of interpretive debates. So there are, all these different mathematical formulations of quantum mechanics, like the Schrödinger picture, the Heisenberg picture, the Feynman sum over histories picture, and these are all mathematically equivalent. Okay, and so you might wonder, how could you ever distinguish between them? Because they lead to all of the same experimental predictions. Okay, but actually one way to differentiate them is in terms of the computational complexity, to simulate what they're talking about. The Schrödinger picture, which has a wave function, the Heisenberg picture, which has a density matrix, these both require exponential time to simulate with a classical computer, but also exponential memory, because you need to write down this giant object. The Feynman picture still requires exponential time, but it only requires polynomial memory because you just keep reusing the same memory over and over to compute more terms in your sum. And this, in fact, is how you prove that quantum polynomial time can be simulated in classical polynomial space. So I like to say that Richard Feynman won the Nobel Prize in Physics for proving that complexity class containment, but okay, I guess there was more to it than that. There's also Bohmian mechanics, which is an interpretation where you say that in addition to the quantum state, there are also sort of real classical trajectories for the particles. Okay, but you so arrange things that these classical particles are just buffeted around or guided by the quantum state in such a way that whenever you look at the classical particles, the predictions of quantum mechanics are precisely reproduced. Okay, so again, by construction, this is experimentally completely indistinguishable from standard quantum mechanics. Okay, so you might wonder, how could we ever, sort of pass judgment on it then as scientists? Well, one thing that we could do, one thing that I did in 2005 is that I looked at what would be the computational complexity of sampling the entire trajectory of the particles in a hidden variable theory like Bohmian mechanics. And I gave evidence that this would be an intractable problem even for a quantum computer. Okay, a quantum computer could, calculate where the particles were at any one time. But in order to get right the correlations between where the particles are at time A and where they are at time B, you would need the ability to, for example, break any collision-resistant hash function, solve the graph isomorphism problem in polynomial time. In general, solve any problem in statistical zero knowledge, if you know what that is. That's not quite up to NP-complete problems, which I wouldn't know how to do even then. But this is more than we think can be done even with a quantum computer. And some of my other work gave evidence that this type of problem is, is likely to be intractable even for a quantum computer in general. Okay, so again, empirically indistinguishable, but theories like Bohmian mechanics are sort of asking for, they're positing a mathematical structure that takes more computational resources to simulate than quantum mechanics itself does. All right, so I wanted to say something about two of Avi's favorite functions. These are the determinant and the permanent of a matrix, which the determinant you've all seen. The permanent is the same thing except without the minus signs. Okay, now you may have also heard that there are two fundamental types of particles. Oh, I'm sorry. Okay, now despite the similarity of their definition, these functions differ dramatically in terms of computation. The determinant can be easily computed, say in n cubed time by diagonalizing the matrix. If you want to be precise, even in n to the 2.373 time. Okay, the permanent by a result of someone you heard from this morning is sharp P complete, which means that it is, Valiant famously showed, it is at least as hard as any combinatorial counting problem. If you had a fast algorithm to calculate the permanent, then you could not only solve NP-complete problems, but count the number of solutions to any NP-complete problem in polynomial time. Okay, now, you may have also heard that there are these two basic types of particles in the universe. Fermions, here's a picture of some fermions, and bosons, here's a picture of some bosons. That's the sun. Okay, so now, the amazing, fact that I still can't get over is that these are, inextricably linked to the determinant and the permanent, respectively. Okay, if you want to know the amplitude for n identical fermions to go from one, input state to some output state, you have to calculate the determinant of an n by n matrix. Okay, for bosons, you calculate the permanent of an n by n matrix. And this is what gives rise to all of the other differences between fermions and bosons that you may have heard of, like that, no two fermions can be in the same place, in the same state at the same time. That's the Pauli exclusion principle. And so they repel each other, and so, fermions are good for making up matter like this. Okay, it's because of these minus signs. Bosons don't have the minus signs, and so they can all pile up in the same state at the same time as, for example, the light from a laser does. Okay, and now one can push, now you may say if determinant is easily computable and permanent is hard to compute, then does that say something about the computational complexity of simulating fermions versus simulating bosons? Well, in fact, it does. So, Avi, once, said 15 years ago, well, what I can say for sure is the bosons got the harder job, right? And so, since then, we've, many of us have labored hard to formalize Avi's wisecrack. And Valiant actually showed that if you have a system of free fermions, that can be simulated in classical polynomial time, ultimately sort of using the fact that the determinant is in P. Turhal and DiVincenzo are physicists who sort of explained that he had been talking about fermions. And then my work on boson sampling with my student Alex Arkhipov 5 years ago basically said that for systems of bosons, you have a hardness result. Even if you just took a bunch of non-interacting photons that you sent through a network of interferometers, that's not a universal quantum computer, probably, but you can then sample probability distributions such that if you could sample those same distributions efficiently using a classical computer, then the polynomial hierarchy would collapse. If you don't know what that means, it's bad. You can take my word for it. Okay, and since then there have actually been experimental demonstrations of this boson sampling, so far with only 3 to 4 photons, but they have confirmed that indeed, their amplitudes are given by the permanence of 3 by 3 or 4 by 4 matrices. If you want to do something that's classically hard, you probably need at least 20 or 30 photons, and if you want to outperform a classical computer, and that might be possible. That's a great problem that people are working on. So the last thing that I wanted to talk about was computational complexity and the black hole information loss problem, which is maybe the single most striking application so far of complexity theory to fundamental physics. Okay, so I'm sure you've heard, if you don't believe me, you can go watch the movie. Stephen Hawking in 1975 showed that black holes are not completely black. They very, very slowly give off radiation. And, according to quantum field theory, this radiation looks completely thermal, which means totally uncorrelated with whatever stuff fell into the black hole. However, that would violate quantum mechanics, which says that evolution is always unitary and reversible, so information is always preserved. Right? Information can't just be deleted from the universe. Okay, so which means if quantum mechanics is to be upheld, then the Hawking radiation somehow has to encode the quantum state of whatever fell into the black hole. Okay, so people have thought for 40 years about how that could happen, and the sort of modern point of view, which came out of Susskind and 't Hooft and others in the mid-1990s, is called black hole complementarity. And what it says is that in the true theory of quantum gravity, whatever it is, the Hawking radiation should just be some kind of scrambled re-encoding of the same exactly the same quantum states that are also at the same time inside the black hole. Now, it's not a copy of those quantum states. Okay, it can't be a copy because in quantum mechanics there's something called the no cloning theorem. It says that you can't copy, an unknown quantum state. And, if someone could see the copy outside and then jump in and then see the second copy inside the black hole, that would violate quantum mechanics. Okay, so it has to be exactly the same state, but it's just being outside the black hole and going into the black hole are just two different ways of measuring that state. Okay, that sounds crazy, but that's, this is what people, have believed for like 20 years. Okay, but then 2 years ago, there was this, what's called the firewall paradox, which said actually this complementarity leads to something that sounds crazy, okay? Namely, if the black hole interior is built out of the same qubits, the same quantum states that came out as the Hawking radiation, well then why can't we do something to those Hawking radiation qubits, so apply some unitary transformation to them. We'll have to wait a while for enough Hawking radiation to come out for this to do this. For an astrophysical black hole, it'll take about 10 to the 70th years. Okay, but assume we have a really long grant. Okay, so we collect all the Hawking radiation. We then route it into a quantum computer. We do some very particular kind of measurement on it. And then, let's say Alice, the observer, traditionally called Alice, does all of this. And then she jumps into the black hole after doing that. And then there's a calculation in well understood quantum field theory that says that by doing this, she should have completely destroyed the structure of space-time inside of the black hole. So when she jumps in, she should not even see a smooth space-time at all. She should, forget about the singularity. She should just die immediately as soon as she hits the event horizon and just reach an end of space-time there. So this is what's called the firewall. Okay? There have been all sorts of, responses to this puzzle. Everyone agrees that it's trivial and it's not a problem, but no one can agree about why not. Okay? And to me, one of the one of the most interesting responses came from Daniel Harlow and Patrick Hayden last year. Harlow is a string theorist. Hayden is a quantum information person. And what they said is that, well, sure, there is some unitary transformation that Alice could apply to the Hawking radiation that would generate a firewall inside the event horizon. But how long would it take her to apply it? And they argued that very plausibly it would take an amount of time which is exponential in the number of qubits in the black hole, which means that we're not talking here 10 to the 70th years. We're talking 2 to the 10 to the 70th years. Okay, which means that Alice would not have made a dent in the problem before the black hole had long ago evaporated anyway. So there's nothing to jump into. So there's no firewall, no problem, right? So, you could say, okay, so, maybe the problem's solved, right? And people say, how could this be? It can't be that, that a contradiction in the laws of physics is okay just because it would take exponential computation time to reveal it, right? That can't be, okay, but that's not what Harlow and Hayden are saying, right? What the firewall problem points out is just a breakdown of effective quantum field theory, which people knew from the beginning is going to break down anyway if you probed at high enough energies, let's say. And what all they're saying is that, not only does quantum field theory break down in the limit of extremely high energies, it could also break down in the limit of exponentially hard computations. Okay, and so this is, it is kind of a radical intrusion of, complexity considerations into, high energy physics. So not everyone likes it, but, I think, people in the quantum gravity community, have been sort of avidly discussing and debating this proposal. Now, but what sort of within my purview is to tell you, how did Harlow and Hayden argue for this conclusion? Well, they gave a reduction, as we do in computer science. They showed that if Alice could achieve a plausible formulation of the decoding experiment that you'd have to do to the Hawking radiation, then, once again, she could break collision-resistant hash functions and solve graph isomorphism and do all those other problems in statistical zero knowledge that seem beyond what even a quantum computer can do. Now, very recently, I was able to strengthen Harlow and Hayden's argument to show that if Alice could do this, then she could even invert any one-way function, which is sort of almost as bad as being able to solve an NP-complete problem. Okay, so I haven't even touched on the huge interplay between computational complexity and condensed matter physics, which is a whole area called quantum Hamiltonian complexity. Here's a picture to just impress you with the depth of what we know about all that. Since I'm running out of time, I think I'll skip it unless there's a question about it. You know, we use complexity to even just to define what we mean by a quantum state being simple or complicated. And that has all sorts of beautiful implications for understanding the ground states of complicated Hamiltonians that, you know, can arise in solid state and in all kinds of many-body physics. Okay, but let me just summarize now with my diagram of reductionism revised. Okay, so the traditional picture of scientific reductionism would be that at the very bottom, we've got quantum mechanics, quantum field theory, general relativity, you know, the fundamental laws of physics. Now, using those, we can build things like semiconductors, we can do applied physics. Using those, we can, you know, integrate lots of them, build computers, and then we can write operating systems and compilers for those computers. And then once we have all of that stuff, then maybe at the top, maybe we can think about what we want to do with those computers or what we can't do with them. Okay, so, you know, this is, you know, a plausible diagram that you can draw of sort of the relationships between these, you know, different fields. But, you know, there is something that we're leaving out. Below physics, you know, there's math, right? You know, that's the bottom of everything. And, you know, what I've tried to show you in this talk is that, you know, in more and more cases, you know, I think of real interest, the kind of math that we want to use, you know, in order even just to understand things about fundamental physics is math related to the limits of computation. All right, so I'll end there. Thanks.